Hello, today I'm going to talk about the ongoing volcanic eruptions, earthquakes, and associated hazards on the Reykjanes Peninsula in Iceland. For 780 years, there were no eruptions on the Reykjanes Peninsula. But in the last 3 years, there have been 8 eruptions on the peninsula. Now, 3 of these eruptions occurred in the mountain called Fagradalsfjall, and they happened in 2021, 2022, and 2023. Then, following this, there were 5 eruptions in a fissure, existing volcanic fissure called Sundhnúkur, not very far from Fagradalsfjall, in fact, and those have happened in the past 6 months. Here we see the early stages of one of these eruptions, namely on the 14th of January 2024, just outside the town of Grindavik. We will discuss that town quite much because a lot of things happened in its vicinity and inside the town. So you see the volcanic fissure here propagating towards the town of Grindavik. Now, these lava flows that erupted close to Grindavik, luckily, they did not reach the town except one. And that's this one here, and we'll discuss it later. It was a very, very tiny one, fortunately, but was still able to destroy a few houses here in the northernmost part of the town. But before we go further, maybe we should look at the geological framework where this current activity is taking place. So the Reykjanes Peninsula, located here in southwest Iceland, is an on-land extension of the Reykjanes Ridge. And the Reykjanes Ridge itself is an extension of the Mid-Atlantic Ridge. So the ridge comes on land here, and then there is a volcanic zone that goes all the way here and to northern Iceland. Now, we usually divide the volcanic zones in Iceland in 3 parts or 3 zones. The West Volcanic Zone, and Reykjanes Peninsula is a part of that in a way, the North Volcanic Zone, and the East Volcanic Zone. Now, it's important to realize that most of the volcanotectonic activity in Iceland occurs in a certain volcanic systems. These are the gray areas here, some of them quite elongated. They are characterized often by fissures at the surface, tectonic fractures, and then, of course, volcanic fissures. But many of them have, in addition, a polygenetic volcano that we call a central volcano, this one here with the black circle. Now, these all have shallow magma chambers. They have magma sources at maybe 1, 2, 3, 4, 5 kilometers depth, in addition to having a deep-seated reservoirs at 10, 15, 20 kilometers depth that supply magma to these shallow chambers. Now, this is very common. There are 28 of these systems, but on the Reykjanes Peninsula proper, that is this part here, there are no known shallow magma chambers, and there are no known polygenetic central volcanoes. The nearest one is this volcano called Hengill here, which belongs to the West Volcanic Zone. But on the Reykjanes Peninsula itself here, there are no central volcanoes and no known shallow magma chambers. Now, the town of Grindavik is shown here. It's located here. Fagradalsfjall is here, and the volcanic fissure that we will be talking about today are mostly located northeast of the town of Grindavik. There are other areas of interest there, like the power plant of Svartsengi that we discussed as well. All right. So why are there no shallow magma chambers and central volcanoes on the Reykjanes Peninsula? Now, the main reason is that we have at least 4, some show 5 or even six volcanic systems here on the peninsula. That means that the spreading, which is around 2 centimeters per year, is divided among 4 to 5 or even 6 systems here. So each system receives very little spreading. The spreading rate of each system is around 0.5 centimeters per year or even less. Now, when you reach down to that level, it's an ultra slow spreading. For example, for comparison, the East Pacific rise, close to the western United States in the Pacific Ocean, has a spreading rate of somewhere between 17 and 18 centimeters per year. So that's a fast spreading ridge as a comparison. So when you're down to 0.5 or 0.4 centimeters per year, the dike injection frequencies, or how often dikes are injected into the crust, is very low. So even if sills are forming like now, even if magma bodies are forming here, they receive new magma through dikes so infrequently that they cannot be maintained. So they have little or no chance to become permanent, shallow magma chambers. Now, the earthquakes on the peninsula are partly related to events within the volcanic systems like Reykjanes, Grindavik, Blaufjöll, and Hengill here, often related to dike injections and sill emplacements. But part of the earthquakes are related to this oblique plate boundary. The oblique plate boundary is on here that goes through the Reykjanes Peninsula here. Now, I should tell you that this Fagradalsfjall, where we had the first 3 eruptions from 2021, 2022, and 2023, is very close to the Sundhnúkur fissure, where the eruptions are taking place here now. Maybe the minimum distance between them is somewhere around 8 kilometers or something like that. Now, on the 10th of November 2023, a 15-kilometer long dike became quickly emplaced along the Sundhnúkur fissure. Now, the Sundhnúkur fissure is an old feeder dike. It's a dike that fed lava flows 2,300 years ago. So this new dike that formed mainly on the 10th of November 2023 clearly followed the existing dike from 2,300 years ago. So we call this a multiple dike, Now, the existing dike made it, of course, easier for the new dike to propagate. That's a thing I've discussed earlier with you in an earlier video on YouTube. But the thing here is that this dike was quite long. 15 kilometers dike is quite long. Such dikes tend to be in Iceland, often 10 or even 15 meters in 15 meters in thickness. So these are regional dikes. These are major dikes. Now, when the dike was breaking its way through the crust, of course, it generated earthquakes, an earthquake swarm, and we can use such swarms to monitor where the dikes are propagating. In this case, it propagated to the southwest and all the way under the seafloor. And unfortunately, also under part of the town of Grindavik. Most of the earthquakes were, of course, very, very small, in magnitude minus or 0, or maybe +1, but a few ones reached the magnitude of 5, which is significant earthquakes. So as I say, we can use the earthquake migration to understand how dikes are propagating in the crust. They generate an earthquake swarm. And we monitor, therefore, the path of the dike, as we did in this case here on the 10th of November 2023. But many dikes, as I discussed with you earlier in the last talk I gave on YouTube, many dikes do not reach the surface. They become arrested. And this dike on the 10th of November became arrested at roughly 0.5 kilometers depth below the surface. And the earthquakes induced by dikes, propagating dikes, are mostly in the walls of the dike and at the tips. Both a tip at the top, the upper tip and lower tip, but they're very much in the tip area here called process zone, and then in the walls of the dike. So we use this to monitor how dikes are propagating. It's very, very important. And we can go into the field and see exactly the same situation in older dikes, like this one here. There are many dikes here. It's one, another one, and many, many dikes. This is in northwest Iceland. It's a tertiary area, so these rocks are maybe 10 million years old or something like that. It's a basaltic dike, quite thick basaltic dikes, many meters thick. And we can see in the vicinity of the dike that it led to either reactivation of existing fractures or generated fractures, and these caused then earthquakes when it was propagating. So this is all related to the pressure, the magmatic pressure inside the dike. It presses on the surrounding walls, causes slip on existing fractures, or forms new fractures, and they generate earthquakes. So schematically, the situation when this 15-kilometer long dike was emplaced on the 10th of November 2023 may have been similar to this one indicated here in a schematic way. So the dike was here mostly at maybe half a kilometer depth, or in some places a little bit more, and unfortunately was under the western part of the town of Grindavik, which is seen here. The dike followed very closely the existing Sundhnúkur volcanic fissure, the one that I mentioned earlier, namely the one that was formed 2,300 years ago. So this dike is using an existing path. It's a multiple dike. Now the volume was very, very large because it's a regional dike. As I say, it may easily be 10 meters or even more, possibly 15 meters thick, and 15 kilometers long, and many kilometers in height or dip dimension. In addition, there are estimates for the volumetric flow rate into the dike, which was very, very high. And these facts and other considerations suggest that part of the dike did not come from the sill that is located underneath Svartsengi, and we discuss in more detail later in this talk, but came from a deep-seated reservoir that we have discovered under the Reykjanes Peninsula recently, mainly under Fagradalsfjall, maybe 10, 12, 15 kilometers depth. That's very likely. However, in this talk, as I explain later, I'm not going to discuss very much the physical processes, the mechanics here. I hope to do so in a later talk. Here I'm going to give an overview of the situation as it has been in the past half a year for all these 5 volcanic eruptions and the emplacement of this dike and how it led to fracture formation inside Grindavik. And that's what we see here. The town of Grindavik, a very nice town, was cut through by many fractures. Now, some of them are pure tension fractures, that is, fractures that just open up. They are usually relatively shallow, geologically speaking. They may be to depth of a few hundred meters, usually not more than that. If they go deeper, they change into what we call a normal fault, where one part, like here, subsides relative to the other part. So in addition to tension fractures and normal fault, there was also a wide general subsidence kind of graben-like subsidence in the area. So here are close-ups of some of the fractures that people could see inside the town. The town was evacuated on the 10th and into early 11th of November because of these events. So no one was living there after that, and no one is permanently living there up to now. So we see the fractures. There are, as I say, somewhat clear normal faults like this one here. So this part here has subsided relative to this one, maybe by close to 1 meter or something like that. Similarly here, and then you have opening. So they're partly opening, tension fracture style, and partly subsidence, relative subsidence, namely fault or normal fault style. Now, not all these fractures are probably related to the dike emplacement. Some of them are just related to the plate tectonic forces that were operating during this rifting episode. So let's look into the field and see what we can see similar to what we are seeing at the surface in Grindavik and its vicinity. Now, if you go to northern Iceland, as I do here, this is the sea level. And because of the glacial erosion, we are looking into an old paleo fossil rift zone at 1,500 meters, 1.5 kilometers depth in the old crust. The crust here is 8-10 million years old. It's not active at all, but we can see similar structures then in a cross section. So we get a 3D, three-dimensional view to what we saw at the surface in Grindavik. Here is a dike. This one is 6 meters thick, so probably thinner than the one that formed in Grindavik under Grindavik on the 10th of November. And in addition, we see a very nice graben here. This is a graben with subsidence of maybe 1 or 2 meters, similar to what we saw at the surface, crossing the roads of Grindavik and in other areas in the vicinity. So we have here normal faults, as you saw there, and extension fracture. So the dikes are extension fracture, they're pure opening, and the crust is simply ruptured by the fluid overpressure. It's the magma itself that ruptures the crust by its pressure. We call it overpressure or driving pressure. Then in addition, we have shear stresses generating these kind of faults. And if they dip together like that, we call them, if normal faults dip together like that, we call them a graben, as we see here. So all these structures can be seen in the field in deeply eroded sections and compared with the active things going on at the surface today. This gives us a 3D view, and you could say we could add time into it, and therefore it's a 4D view, really. So, following the dike emplacement on the 10th of November 2023, then in a rapid succession, there were 5 volcanic eruptions. I remind you, the dike on the 10th of November did not erupt. There was no eruption then. But on the 18th of December, an eruption started. And here is the volcanic fissure very early on in the eruption. And you see this a nice, what we call anachelon arrangement. So the fractures are discontinuous and offset, laterally offset here in this area. This is the very early phase of the volcanic fissure, which was around 3.5 kilometers at its maximum length. Very quickly, the activity becomes focused on certain parts of the fissure. And in addition, we see that, or the estimates indicate that the volumetric flow rate was somewhere between 100 and 200 cubic meters per second. So not much, not very much. Now, I draw your attention to that because we come later to much higher values. This was the first eruption in December, 18th of December, 2023. It lasted only a few days, came to an end on the 21st of December. 2023. The second eruption was very similar. It started on the 14th of January 2024. The main fissure, seen here very early on, was 900 meters long. It propagated a little bit through barriers. So already then it had been decided to build lava protection barriers to protect the town of Grindavik and the power plant here of Svartsengi and the Blue Lagoon and so on. So it had not been quite completed, but much of it had been done already. And part of the fissure went through, but didn't seem to pose any great risk to the houses of the town of Grindavik. Unfortunately, however, a little later, a tiny kind of finger-like fissure formed, tiny fissure, just 100 meters away from the northernmost houses, unfortunately, and lava was able to flow down to the houses, as you see here, and destroyed a few houses here. So far, this is, of course, the only destructions of built structures, apart from some roads have been destroyed. So far, there hasn't been lava flowing into Grindavik, except this tiny case here. And now the town is very well protected by major protection barriers, as I'll mention later in this talk. Now, this again was a short eruption and came to an end on the 16th of January. Very similar duration as the first, as the other ones. Now, the third eruption began on the 8th of February and again followed similar pattern, namely it lasted only 2 days, came to an end on the 9th of February. The volumetric flow rate was of the order of hundreds of cubic meters initially. Now, be careful here, please. These volumetric flow rates are, of course, estimated, and these are what happens in the beginning of the eruption. Very quickly, they decline, as I come to in a moment. They decline very, very quickly. So this one was short-lived as well, and starting on the 8th of February and ending on the 9th. Then the fourth eruption, and there we went into a different situation. It started on the 16th of March, as you see here, and it was with a fissure maybe 3.5 kilometers long initially, but as I say, you see the initial phase here, or early phase here, offset here, fractures, fissures, and lava flowing from them. Initially, the volumetric flow rate was higher, probably up to 1,200 cubic meters per second. And then, of course, that was only the beginning phase, because very quickly it declined first to 100 cubic meters per second after a few hours, and then to 15 cubic meters per second on the 20th of March, then to 8 on the 27th of March, 4 on the 8th of April, and finally somewhere around 1 cubic meters per second or even less until the eruption came to an end on the 9th of May. So this eruption lasted 54 days. Now compare this with the early 3 eruptions, all lasting only a few days. So here is a certain change, and it probably related to the mechanism and may also be related to where part of the magma is coming from. The fifth eruption began on the 29th of May in 2024, should be here, not 2024. And the fissure reached the maximum length around 4 kilometers. In the first hour, probably up to 1,500 meters, cubic meters per second. So this is again quite much more volumetric flow rate, or effusion rate, as we often call it in volcanology, than in the first 3 eruptions. Now, this eruption is still ongoing now as I speak on the 18th of June 2024. Now, so here is an overview, schematic one, of what has been going on in the area and the location of the main places of interest and in a way worry. So we have the lava flows from the eruptions from December 2023 and then January, February, March, April 2024, and the still ongoing eruption May, and that one started on 29th of May and is still ongoing now on the 18th of June as I speak. Now we see also here, which is very, very interesting and important thing, we see the barriers, the protection barriers. They have been built up around the Svartsengi geothermal power plant, and underneath that power plant is a sill, or in fact a multiple sill formed over the last few years. And then we have the Blue Lagoon, it's a famous touristic place, and the town of Grindavik and the barriers protecting that town, very nicely showed. And this map here was made on the day of the eruption of 29th of May. So it shows in a very schematic way the fissure there. It shows some of the older fissures from the earlier eruptions and some of the lava flows from all the eruptions. So you see here, most of the barriers are already made, but some are being constructed when this map is made. So mostly they are made, solid line, and broken line is those under construction. So, as I said in the beginning, to discuss the physical principles that control these eruptions would require entirely new or different talks. So I'm not going to do that. I can say, though, that the processes are obviously somewhat complex because, first of all, there have been several sill emplacements underneath Svartsengi in the last several years, around the depth of 4 kilometers. Now, why do sills form in rift zones? They form usually where there's a contrast, the so-called mechanical properties between layers. So often they form under, say, stiff or high Young's bodies, lava flow at a contact with a softer layer like hyaloclastite, basaltic breccias that we call hyaloclastite. They're very common on the Reykjanes Peninsula and in the volcanic zones of Iceland in general. So they form there. Now, if this kind of sill would receive frequently new magma through dikes, it could develop into a shallow magma chamber. But it's very likely that this episode that we are witnessing now will last maybe some years, and then nothing will happen there for tens of years or even hundreds of years or more. So then this will solidify and not have any chance of becoming a permanent or long-lasting shallow magma chamber. So it seems to be that part of these eruptions, at least the early ones, and probably all of them, but part of the magma is coming through a dike from great depths, maybe 10, 12, 15 kilometers depth, up to the sill at 4 kilometers depth, flowing along the sill and then up through a dike that is parallel with the old 2,300-year-old dike, Sundhnúkar, and the Sundhnúkar fissure. So let's look at that in detail as we could see it in the field. So I show you here a photograph. This is of course very, very schematic, but I wanted to show you a real sill in Iceland. So this is a sill. The sill cluster under Svartsengi is probably thinner than this one. You can see the scale here, the farms in East Iceland for scale. And you see the sill is ending here, is rounded. This is the tip of the sill. So the idea is that magma comes from great depth, 10, 12, 14, 15 kilometers depth, along some sort of a dike, meets with the sill, or the sills, flows laterally, longer distance than shown here, and then meets with this existing dike, the one from 2,300 years ago, and there flows up to the surface. So this is the basic idea indicated with these white arrows. So vertically, horizontally, and then vertically again. Now you see all these lava flows and sills here are tilted, are dipping, as we say, around 8 degrees. That's later. Initially they were horizontal, but this dipping or tilting came later due to general sucking effect of the lava pile in eastern Iceland. So they become non-horizontal or slightly dipping with depth in the lava pile. So we are here at 1 kilometer depth, but of course the sill in the Reykjanes Peninsula, the ones we are talking about now under the Svartsengi geothermal power plant, is at around 4 kilometers depth, but similar to this one, probably thinner and possibly more extensive. Now sills can either be circular in plan view, or they can be so-called tunnel shaped, so elongated in one direction. The one under Svartsengi is presumably circular in plan view, as I will show you in a moment. So here we see one of the basic arguments for why there is a sill or cluster of sills under Svartsengi. Svartsengi is located here. All this lettering here is in the words here in Icelandic, but I explain what I mean. So these are geodetic measurements indicating that the land has been rising. We call it inflation, and the greatest inflation or greatest doming of the land is here in the red area, less in the yellow, and still less in the green one. So this area has been uplifted, and this uplift is presumably related to sill emplacement. Now this image here is from the year 2023 and before either the dike 2023 and the 10th of November, and of course before the eruptions in 2023 and 2024 happened. But it shows the same pattern as we see again and again. Magma is coming in and the sills are being emplaced, and the idea is that the sills or sill is used partly as a path for the magma that comes then up in the volcanic fissure outside the sill, or at the margin of the sill, really outside the sill. So the sill is supposed to be at least part of the source of the magma for the eruptions. Now there are many hazards associated with volcanotectonic events like we have seen now in the Reykjanes Peninsula in the last 3 years, and particularly now in the last half a year. Now potentially, remember, actual damage has been little as regards the lava flows, but of course there has been much damage of the houses in Grindavik due to the fracturing. But the potential damage includes, of course, destruction due to earthquake fractures. Then, of course, there can be gas pollution, groundwater pollution, if the lava flows go into groundwater resources, and then lava may destroy both infrastructures such as roads, as seen here in June 2024, this very recent photo, and possibly might, of course, destroy power plants or urban areas. So far, this has all been protected. You see the barrier here, and they're working on it here. So the barrier is here. The lava is coming up to the barrier here. So the power plant and the Blue Lagoon are protected from the lava flow here. But of course, the road has been well, not really destroyed, but damaged here in this part. Most of the road is of course still fine. So let's move on and discuss a little bit more of these hazards. So the protection barriers, as I say, they have been of great success. Here is a schematic illustration of the barriers around the power plant of Svartsengi and then the Blue Lagoon. And then they've built also barriers around Grindavik. Here you see the volcanic fissures. So how effective have they been? Well, they have been very, very effective indeed. So here we see the barrier around part of Grindavik. And you see the lava. And this is from the lava. This photo is taken on the 30th of May. So this is the lava from the eruption that started on 29th of May, 2024, and still ongoing. So the lava flows down here. You see the front of the lava flowing down here. And yes, it destroys the part of the road. We've discussed that earlier. But the barrier here is protecting the town. So it's a great success. Now, the barriers initially were 3 to 4 meters high, and now there are plans to build them in some places up to 6 meters. But they have been great success here, and we learned a lot from this activity. You see this even better here. So this image is from the 30th of May, so one day after the 29th of May eruption started. This is the fissure, the volcanic fissure from the 29th of May eruption. These are the lavas. The black is the lava from that eruption. Also shown are some of the older lava flows from the earlier eruptions in these episodes, also from 2023 December to up to March 2024. And here you see the little one that came into the northernmost part of Grindavik and destroyed a few houses. And here you see what went through the barriers in the same eruption. But very clearly, the barriers today, they protect the town extremely well, and similarly protect the power plant here and the Blue Lagoon. So this has been a great success. So if you look at it in a wider perspective, we are talking about volcanic eruptions happening on the Reykjanes Peninsula, where there hadn't been eruptions for 780 years. Now, this may mean, based on historical information, this may mean that there will be some eruptions from time to time over the next years. So far, they've all been very small, and generally eruptions on the Reykjanes Peninsula are small. They are small, and they are usually effusive, meaning there are lava flows, no explosions, no explosive eruptions. You could, of course, have some explosions if it goes into the sea, but we are not looking at that at the moment. So, does this activity pose any threat to the capital area of Iceland? The capital area is Reykjavik and the surrounding towns, and you could say also, does it pose any threat to the main international airport in Iceland? Now, obviously, and luckily, the airport is built on a relatively high ground there and comparatively old rock, so this is not an active area at all. And the airport seemed to be safe, absolutely safe. Similarly, the town of Keflavik and the town of Njarðvík. Then we have the capital area. Now, Reykjavik is definitely outside any volcanic system. Reykjavik is not a volcanically active area, so you don't expect at all to have volcanic eruptions in Reykjavik. So the question is, can any lava flows come from other parts of the Reykjanes Peninsula and towards Reykjavik? Now, if that would happen, obviously the flow would have to be very long, go from one of the volcanic systems here on the Reykjanes Peninsula and flow towards Reykjavik. And the experience we have now indicates we would, of course, build protective barriers to divert the flow away from Reykjavik and the capital area. There are other aspects that needs to be looked into. For example, There could be possibly situations related to the groundwater resources of the capital area. And they are here, so they are close to Reykjavik, within older lava flows. And all of these things indicate the same, namely that if there is any likelihood of any lava flowing, and they flow then relatively slowly towards the capital area, people are going to build barriers, protective barriers, to divert them. So we could say that as the situation is now and likely to continue, it is very unlikely that Reykjavik itself and its surrounding towns is going to be under great hazards or risks. But the main thing is that we have learned a lot so far, and we have learned how effective these barriers really are in protecting urban areas and important sites. And surely that knowledge will be used to protect the capital area if needed sometime in the future. And with these words, and showing you the volcanic fissure here on the 30th of May, very close to the power plant, but still being protected, the power plant being protected by very efficient barriers, is a good way to end this talk. So I say simply, thank you very much indeed, and bye-bye.